Hi guys, my name is Hari and this is Project Directory, where we'll be focusing on technical videos related to projects that I and the OSS community have built. Today, I'm going to tell you why Rust is not just another programming language. It's a paradigm shift in how we think about building reliable software. The structure of this video is inspired from one of the most helpful Rust YouTube channels called No Boilerplate. That being said, this talk moves fast. Everything you see here will be available as an open source markdown document on my GitHub, link in the description. Here's what we'll be covering today. We'll learn more about what exactly it means to be a low-level language. We'll have a lot of comparisons with other languages. I'll then try my best to explain how Rust differs from traditional programming. We'll talk about what and where Rust is used. We'll look at basic code snippets and finally talk about how you can start learning Rust. Consider this a speedrun of Rust's language features. Currently I'm at college doing my masters on computer applications, and my fellow classmates and colleagues at internships do not have much experience shipping code to production. Even so, there are things that eventually every software developer needs to learn. How to write clean, maintainable code, how to write test cases for each level of abstraction, and so on. I have questions for the generic software engineer who already has a bit of experience. How many of you have debugged a segmentation fault at 2 am? How many have traced a null pointer exception through 5 layers of abstractions? How many have shipped code confident it works only to watch it crash during production? We accept this, we build monitoring systems, write extensive tests, and pray that our error handling catches everything. What if I told you there's a language where an entire class of these bugs simply cannot exist? I have a simple question here. Is this code correct? This is just a basic snippet of a function in JavaScript that takes a number as a parameter and returns a +1 value of it. Is this code correct? As software developers, we often need to think about times at which a particular part of the software that we ship might fail. That is why we think about edge cases and write test cases to ensure every possible input is handled carefully. So my rephrased question would be, how can this function fail? Or what is the scenario that this function might fail? Let me think of a few scenarios. Is n always a number? What if I pass in a string? How large is n? Can I give it a value so big that it breaks my database layer at 2 am? Could n be modified while we are reading its value? What about negative numbers or floating values? Does this function accept all of those values? Although as software engineers we would think of all of these and write test cases for the function to ensure that the increment function always works as intended, and that would be right. But even so, with programming languages similar to JavaScript, there is one thing common among them. That is uncertainty. A simple intro on Rust. Rust is a systems programming language built by the Mozilla team that places a huge bet on memory safety without a garbage collector. For rookie devs, think of it as C++ performance meets Python-like ergonomics. It has a very powerful type system that makes invalid states unrepresentable. Here are some features of Rust, which we'll be talking about briefly later. And it has the best compiler error messages that you've ever seen. The compiler doesn't just tell you what is wrong, it tells you how to fix it. So here's the code snippet for a hello world program in Rust. Familiar syntax, C-like, nothing scary here. But watch what happens when we get more complex. Rust has a well-defined, strongly typed system similar to C. But Rust doesn't always explicitly ask the programmer about the type. Rust's compiler tries to infer the type on assignment and holds you to that rule. Once a variable binding is defined with a value of a type, it cannot be assigned a value of another type. Here's another program with seemingly simple syntax again. All we do here is read a number from the user, print it to the default terminal, ask the user for another number and assign it to the same variable, and print it again to the console. I have used the external crate text.io for ease of console input here, but Apart from the necessary abstraction there, this code looks valid and should run. That is until you hear the compiler throwing an error at compile time. This code will not compile. Let's look at the exact compile error. Here we have the very detailed compile time error for the program from Cargo, Rust's build tool and compiler. It tells us that we tried to assign a new value twice for a variable that is immutable, and it asks us, the programmer, to explicitly define the variable as mutable. Variables are immutable by default in Rust. You opt into mutability. This single design decision prevents countless bugs. Rust is fast, really fast. In the computer language benchmarks game, Rust matches C++ performance and is 10 to 100 times faster than Python and is 2 to 5 times faster than Java and uses a fraction of the memory. And you get the speed without sacrificing safety. Let's compare some of those languages directly with Rust. Python is beautiful, we all love it. It's a language of data science, machine learning, scripting. The syntax is clean, the ecosystem is massive. But Python is slow, really slow. Your API handles 100 requests per second. A Rust version, 10,000 requests per second. Your data processing script takes 10 minutes. The Rust equivalent, 10 seconds. And the memory usage? Python's interpreter overhead means that even a simple script uses 50 MB. Rust just takes 2 MB. Java dominated enterprise development for decades. It's fast enough, the JVM is battle tested, the ecosystem is enormous again, but Java has problems, starting with memory. Your Spring Boot microservice uses 500 MB at idle, a comparable Rust service 5 MB. Startup time. Java needs to warm up the JVM. Your serverless function has 2 seconds of cold start. Rust, 50 milliseconds. Null pointer exceptions. Java's billion-dollar mistake. Every reference might be null. In Rust, there is no null. If something might not exist, it's wrapped in an option type. The compiler forces you to handle it. C++ is the king of systems programming. It's what operating systems, game engines, and browsers are built with. It gives you complete control, zero overhead, maximum performance. But that control again comes with a cost. With memory safety, in C++, memory bugs are your responsibility. Data races. C++ has threads. You can share data between them. But good luck debugging when 2 threads modify the same data. Modern tooling. C++ has CMake, Make, and dozens of build systems. Package management is a nightmare. Rust has Cargo, one tool, builds, tests, documentation, dependencies, everything handled. Rust is what C++ would be if we redesigned it today with 40 years of hindsight. Some of the features of Rust include memory safety with a safety net. Rust's job is preventing the most common bugs of languages like C and C++. It stops use after free, buffer overflows, and those null pointer exceptions all at compile time. If the code has a memory error, it simply won't compile, it simply won't build. Zero cost abstractions mean that you get all the convenience of a powerful high-level language, but the resulting machine code will always be just as fast if you had written it in assembly. No trade-offs here, just performance. A type system that knows your business. Rust's type system is incredibly powerful. It uses algebraic data types to help you model your problem's domain so precisely that you can literally make invalid states unrepresentable. If it compiles, it's correct by design as well. Explicit error handling. No more nulls. This is the big one. Rust has no null. That eliminates an entire class of painful runtime errors. Instead of guessing if a value exists, the compiler forces you to deal with uncertainty head-on using 2 types. Option type for values that might be missing, or the result type for operations that might fail. You must handle every success and failure case. The compiler is your quality control, making sure nothing slips through. Composition with traits. Rust approaches object-oriented programming without the complex inheritance hierarchies. It's built on composition, which is often a better way of structuring your code. We have structs that hold your data and traits that define their behavior. You mix and match traits onto structs to build complex systems from simple, focused pieces. It gives you the benefits of OOP, but keeps the codebase flexible and maintainable. Writing concurrent multi-threaded code is notoriously difficult, except in Rust. The language's famous borrow checker prevents the most dangerous kind of concurrency bug, which are data races. You simply cannot accidentally share mutable state between threads. If your concurrent code passes the compiler, you can be absolutely confident that it is thread safe. Now on to what you can build using Rust. It's mostly used for systems programming, which is operating systems, file systems, device drivers, but that's not all. Rust is a mature programming language. We wouldn't be talking about it if it was a niche product. So the possibilities are truly endless. You can build desktop apps using native crates for each platform. Or you can use one of the amazing cross-platform libraries we have to build across platforms. Rust can even help you build apps for mobile as well, using the Tori framework. Write blazingly fast APIs and microservices using the Rocket crate. Write scalable frontends for your web apps using the U or Deoxys frameworks. Maybe you're a game developer looking for more control. Look no further. The Bevy engine makes it easy for new developers to build on top of their own game engines. If you don't want to write a game engine yourself, the Godot engine now has full support for scripting using Rust alongside Godot's script. Maybe AIML is your jam. In that case, various crates like the CUDA standard crate allows devs to take advantage of GPU hardware for parallel processing. If you're building software for embedded systems, Rust's rich ecosystem of crates allows devs to maximize the use out of hardware using crates like ESP-RS. This is one of the reasons why Rust has become the most loved language for developers to write code in since its 1.0 release. And it all relies on one huge promise that Rust makes. Your code will not crash. Rust ensures this by means of its two main principles, the ownership and borrowing pattern, and the strong and rich type system. Rust ensures that if you satisfy the compiler, your code will not crash at runtime because of memory errors. This means no more dangling pointers, use after move errors, memory leaks, etc. Let's look at an example to demonstrate the ownership and borrowing model. Here's where Rust gets interesting. Here's a simple program that has two variables, x and y, and x is defined as a string type, binding the value hello world. It is printed once before the variable is passed on to y, and then I try to print the value of x. This code will not compile. The Rust compiler tells us that this is a case of use after move. What essentially is happening here is x and y are variable bindings which are owners of their particular values. Variable x is the owner of the value hello world. When one variable is assigned to another, the ownership of that value gets transferred to that another variable, which in this case is y. And that means x is no longer valid and cannot be used. This is the crux of the ownership system. It's a simple design change that helps developers avoid many memory bugs at compile time instead of runtime. You cannot use a value that has already been transferred to another part of the program. Now this presents another problem. How do we fix that error? This is where the borrowing model comes into play. This is a simple change but a meaningful one. Now instead of transferring ownership to the value of over to y, I'm telling the compiler that you can borrow the value of x to read it, but the original owner of the value is still going to be x. That is what the ampersand or the and symbol means. It means that the value of x is borrowed by y, but x still retains the ownership of the value. This code now compiles with no error. Veteran developers might recognize this as an explicit way to define pass by reference and pass by value by code. Rust's smart design makes you think before making each and every choice, because at the very least, for programs that care about their runtime performance, small things like these make a large difference. This is how we pass by value in Rust. Any value can literally be cloned and passed as a value. Now x and y hold different strings with the same characters and are owners of each value respectively. Rust isn't difficult, it's just unfamiliar. It's a very smartly designed language that relies on limiting the developer's freedom to achieve that greatness. This can seem counterintuitive for people moving from other high-level languages like Python and JavaScript, because when they code in JavaScript, they make a change and boom, the hot reload immediately makes the change and shows the change on the UI, regardless of whether it's functioning correctly or showing an error. Tris from No Boilerplate put it correctly when he named this approach error-driven development. Not that there is anything wrong with that, but compiled languages have to make the sacrifice between quick iteration and maximum performance, as the overhead that features like hot reload bring is simply not worth the performance decline. In Rust, if you iterate quickly without thinking about your actions firsthand, the compiler will shout at you. There is only one rule to writing good Rust code: obey the compiler. Do what the compiler says, be nice to it, and it'll be nice to you. Tris calls this compiler-driven development. Let's do a fun example to show how helpful a compiler can be. We are going to refer a previous snippet of code that we had, the increment function in JavaScript, and simply paste it onto a fresh Rust file. The compiler immediately panics when we run it with cargo run with an error. Not only is the error clearly given with the line and character address, the compiler is generous enough to help us with the error firsthand. It asks us to correct the syntax by providing us the correct syntax. Onwards. Rust is explicitly typed wherever the compiler cannot infer types on its own. It asks us to declare its type by giving us all the methods to do so in this helpful panic message. Let's add the type as int for an integer. Primitive types like integers and floats are declared with their bit sizes, so the programmer knows the exact size each integer value would take up in memory. We haven't specified the return type. Rust tells us how to do so in its syntax as well. Finally, we'll need a main function to test this out, so let me also write that. And I'm going to write it in a similar fashion to JavaScript. Again, finally, Rust informs us the syntax of the print line macro. And now we're done. With none of the uncertainties that we had earlier too, thanks to Rust's robust type system and the smartest compiler in the business. 9 years. Stack Overflow runs a survey every year asking developers what languages they love working with. Rust has won 9 years straight. Not most used, most loved. The people writing Rust, they're not going back to C++. They're not going back to Java. And it's not just hobbyists voting in surveys. Microsoft is rewriting parts of Windows in Rust. The Linux kernel, 30 years of pure C, now accepts Rust code. Amazon's running critical AWS infrastructure on it. These aren't experiments. This is production code handling billions of requests. Some of my favorite open source projects are written in Rust, like the Helix editor, which I use to code Rust and also write the script in, Western, my Windows terminal replacement, UV, a faster, simpler pip replacement for Python, and terminal-based coding tool called Codex, developed by OpenAI. All tools developed using Rust. Now you want to learn Rust? Where do you start? First, install Rust. Goes to rustup.rs, one command installs everything. 5 minutes later you have Rust, Cargo and the entire tool chain. Mac, Linux, Windows, doesn't matter. Second is read the book, which is the recommended way for developers to start learning Rust. It's available at doc.rustlang.org/book. It's free, it's comprehensive, it's actually well written. You'll build a guessing game, a command line tool, a web server. By the end, you'll understand ownership, borrowing, and lifetimes. These are the concepts that make Rust different. Third, rewire your brain. Rust syntax will feel overwhelming at first, especially coming from Python, JavaScript, or dynamically typed languages. The compiler will fight you. The Rust compiler catches bugs before you run the code, not at runtime, at compile time. Rust is different. It's not Python with types, it's not safe for C++. It's a fundamentally different way of thinking about memory and ownership. If you approach it expecting it to work like other languages, you'll struggle. If you approach it ready to learn, you'll discover something powerful. The learning resources are excellent. The book teaches concepts step by step. Rust by example shows working code for every pattern. Rust links give you exercises that fail until you fix them, learning by doing. The community is welcoming, the documentation is thorough. The compiler error messages are the best you've ever seen. This is a comprehensive list of things that maybe you can explore on your own about Rust and its different features. The more you explore, the more you learn. Here are some YouTube channels to learn and stay curious on your Rust journey. You won't master Rust in a weekend, but you don't need to. Start small, build one thing, then another. Thank you for watching. See you in the next video.